Hello, everyone. Thanks to all for coming. I will be talking about Tenet. It has been my main project for the last year, and also about some of the related libraries that we have been working about at BSc. So first of all, getting registered in the general registry of Julia is like a speed race. So there is already another library that's called Tenet in the general registry, but ours is not that one. So we have our own registry. So if you want to use these or any other related libraries, please just use our register. Don't worry, I can pass the slides later. So there have been already some talks about tensor networks. I'm going to give a very brief talk about that. But in general, tensor networks, I'm going to go a little bit fast, but in general, tensor networks are a graphical description of multilinear equations like this one. So for example, here in this graph, nodes are tensors and the edges are vector spaces, are the tensor indices. So this graph is actually equivalent to the equation that you can see in the right. What you can do is, so in order to compute this summation, it will require a lot of for loops. You don't usually do that. You do something smarter. That is that you do the sums in some order, and this order is very, very critical for your performance. So for example, if we start with M, we just contract the M, and when you contract the nodes, you do perform this operation. This is equivalent to graphical notation to actually sum them, like literally fuse the two nodes. And you can go actually continue recursively until you get one number or another tensor. And this is the number that you are actually looking for. This is a great formulation actually for things like, for example, quantum computing or quantum mechanics in general. But it also, like Matt and other people have been talking about, you can do a lot of other cool stuff. But the problem is that actually looking for the optimal contraction path is an NP complete problem, so it's very hard. And there are a lot of packages right now in the Julia ecosystem trying to deal with this problem, like to expressing all this. Ainsum, Tulio, Tensor Operation, Amazon, iTensors. And it's great, they are great packages, but all of them actually assume that the users know like they can type all this equation by themselves. But okay, what happens if you have a graph like this? Okay, you run out of letters actually. This is actually not very useful to actually type an instrument string like that. So in order to deal with this kind of graphs in large scale, because at BSc we have supercomputers and we are interested in large scale tensor networks, we developed this library that is called NExpressions. That it's inspired in the Python library of the ecosystem. It's inspired in Opti, Ainsum, and Cotegra. They deal with very large tensor networks. The idea behind that is that you can see a contraction path as some data dependency tree. And this data dependency tree, you can see it also as an expression in Julia. So we created our own expression that basically the head is the output indices and the arguments, the input arguments are the input tensors or some other n expressions. And with this kind of structure, it's actually very easy to view it as the contraction, like the data dependency of the computational graph. And you can actually see any heuristic or search like an optimizer, and you can also do further optimizations or actually do things like, for example, to use this heuristic till this moment, till you get this depth in the tree, and then use this other heuristic or this optimization. Also, this structure is very useful for getting like results counters, like for example, okay, how much flops I'm going to need to actually compute this, or what are the sizes of the intermediate tensors. So for example, you can do some tensor slicing. If, for example, you already have this n expression and you know that it's not going to fit into your node, in your cluster, so you need to slice the tensors. This is like some kind of blocking scheme. And in n expression, we already implemented as an heuristic for searching for them. This kind of tensor slicing is like you see, is actually taking one of the summations of this whole equation and taking it out. Taking it out is not actually doing it separately, it's just doing it, but one of these summations you're going to do it distributively. So you're projecting this index to some basis, and you're copying each of these bases or each of these projections to different nodes, and you run them in parallel. You get an increase, an exponential increase in parallelism. If you choose the indexes wisely, it reduces your memory usage, but also you get an overhead. So this is not free lunch, but it's great for actually getting like easy parallelism. And also, NExpression is also thought as a research library. So if you are researching on contraction path heuristics or in tensor slicing search heuristics, it's a great tool to actually see what your heuristics are doing. So this is, for example, before and after of one of these slices. You can see that the NExpression is actually much smaller. And so Tenet is the library that actually gets on top of NExpression to actually describe tensor networks. It's inspired by Quim and Python library. What is very special and different to other Julia libraries in tensor networks is that we don't have different, like classes for different kinds of tensor networks. We only have one tensor network structure, and the type of tensor network is actually fused into the type system, into the generic parametric type system. So here, where you see the unsuch thing. Because, like, for example, if you have a quantum tensor network, you need information about sites and about, direction. You need some extra metadata, a part of the graph. So you include this also in part of the type system. And you can also inherit this with this metadata and constructor. So it's more or less like the Julian way you have some field inheritance. So this is a very easy way to actually expand the amount of quantum tensor networks that you have, like MPS or PEPs. You can also already have this site information, and you can very easily fuse with an MPS, for example, to have an MPS and an MPS contraction. You don't really need to deal about what are the indices names. Also, another cool thing that we implement, I think that any other library implements, is local transformations. This is kind of similar to ZX calculus, not really. It's like a numerical thing. In Quim, they implement it a lot. The idea is to simplify the tensor network to get an equivalent tensor network that actually is much easier to look for the contraction path, or you can see for some symmetries, and it's, in general, much easier to compute. And also, we are also very interested in expressibility for our users, because a lot of them are physicists, are not computer scientists. But we are in a supercomputing center, and we actually are very, 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 we care a lot about performance. So I think the best way to use this is to give a lot of freedom, a lot of expressibility, because it's not about doing a tensor network simulation, but about designing experiments. So you should have like good defaults by default, but you should have also the capability to tune the contraction in your own way. So, for example, this is the Google Quantum Advantage experiment in less than 15 lines of code, thanks to our care in these kind of things. So, for example, you can actually distributively search for the contraction path and also do a contraction of the different slices distributively by just adding a couple of lines. And in the future work, we are actually already have some quantum tensor network implemented, but we want to implement all of them, or all of that are known. We're also interested in some other application of tensor networks aside of quantum tensor network, quantum mechanics, like SAT and combinatorial problems. And for expressions, we're implementing automatic differentiation. It's already implemented, but we are fixing some bugs currently. And also something that would be very interesting about compilable expressions, because this expression is like some expression, like it should be very easy to actually compile it to a Julia code, or actually using GPU compiler to actually compiling it to, for example, XL, that is the intermediate representation that JAX uses. And thank you all for listening to me. We're dealing already with that. So the question was about distributing tensors, like the inner part of the tensors. Yeah, this was a very easy example that shows the expressibility. You can do it because we already have tried that with block arrays, so you can use block arrays. And I have already talked to Julian Samaru for using Dagger or these like kind of things. So yeah, because the good thing about Tenet is that it can impose you the array types. So you can use any array type. So you put like a distributed array type inside Tenet, it will work.